Hi everyone, my name is Suborno Isaac Berry from Berry Science Lab, and today we're going to be fully deriving the Bohr equation in one lecture. So, to start, what is the Bohr equation, and where are we coming from? Well, you probably remember that the hydrogen atom is one proton with one electron orbiting around it. Now, what's the potential between these two? Well, the force by Coulomb's law is, well, the magnitude of the force is 1 over 4 pi epsilon naught r squared multiplied by q1, q2. And so, since the gradient of u is the negative force, that means that u is equal to, since the gradient is kind of like just taking the derivative with respect to with respect to r, we get u is equal to minus 1 over 4 pi epsilon naught r q1 q2. And in the case of the hydrogen atoms, what is q1 and q2? Well, the charge of the proton is e, unit charge. The charge of the electron is e. So that means that this is just minus e squared over 4 pi epsilon naught r. Oh, wait a minute. This is wrong. The charge of the proton is e. The charge of the electron is negative e, which means that this is positive e squared over 4 pi epsilon naught r. That is the potential of the hydrogen atom. Now, you may recall that when we were trying to take the Schrodinger equation from 1D to 3D, we had to introduce spherical coordinates because many potentials depend solely on the radius. Now, if we were to convert this to Cartesian coordinates, it would look not just a lot nastier, but it would also be totally impossible to execute separation of variables with this thing in the way. Which is why we want u to depend on one variable instead of three. We don't want So we don't have to deal with a partial differential equation of three variables. We can deal with an ordinary differential equation of one. So what? So what equation did we get after using separation of variables? Well, we got three equations: r, theta, phi. We solved this one. We solved this one up to a few constants, but this one is unsolved because it depends on the potential function. So today we're going to see what happens when we plug in the potential function for a hydrogen atom, and it's going to tell us why atoms have energy levels. So this is just e squared over 4 pi epsilon naught r. Now, what is the radial equation? In general, without a potential, this is minus h bar squared over 2m. That's just a constant. Don't worry about it. Psi r double prime. That is a function. The function that we're solving for, in fact. So do worry about it. Plus minus u of r. That is the potential function. We want to worry about it. Then minus h bar squared over 2m. L times L plus 1. This is just a constant. This is the separation constant. Don't have to worry much about them for right now. Divided by r squared. That is a function. You should worry about it. Multiplied by psi r is equal to e psi r. And you probably realized just now that this looks eerily similar to this equation. And that's because it's almost the same exact thing. The only difference between radial coordinates and regular old x dimension is the centripetal term. But as we will see soon enough, the centripetal term actually makes a world of difference. So what happens when we work around the centripetal term? First things first, it's time to plug in, let's erase that equation. first things first, it's time to plug in the actual potential. So you get minus h bar squared over 2m psi r double prime plus minus e squared over 4 pi epsilon naught r minus h bar squared over 2m L times L plus 1 over R squared. Psi R is equal to E psi R. Now your first instinct is probably to bring this over into the psi R factors. So let's do that. So now, what else can we do with this? Well, this is practically impossible to approach using normal methods. I mean, what can we do? We can try using power series, but these terms are going to be a big problem to work with anyway, because power series have constant terms. And even if they don't, they still have linear terms. And these linear terms aren't going to get canceled out by psi r double prime. Psi r double prime is just a polynomial, which means that these nasty things are still going to stick around. There's going to be no way to get rid of them. Hence, we can't use power series. Well, not yet, anyway. So, what can we do? Well, first thing first, let's condense all of the constants into one meaty blob. So I'm going to set, I'm going to divide both sides by e, and I'm going to set kappa is equal to the square root of minus 2me divided by h bar. So you get this psi r double prime plus, and remember, psi r double prime, well, no, I can't say that yet. We haven't done the substitution. I'm spoiling it all. Minus h bar squared over 2me L times L plus 1 over R squared minus 1 psi R is equal to 0. Okay, now we're going to let rho is equal to kappa times R. So what is this going to do for us? Well, it's going to make things substantially cleaner. This is going to give us minus 1 over kappa squared. So, actually, no, not minus 1. This is just going to be 1 over kappa squared multiplied by psi r double prime. And keep in mind, this is still psi r double prime of r. We haven't done the substitution yet. So what happens when you do make the substitution? Well, just to get a grip on it, let's take a very simple function like 2r plus 1, and let's suddenly say rho is equal to kappa r. Then so let's say psi r is equal to 3r squared plus 2r plus 1. Then when you take this substitution, that means that this is suddenly going to become 3, well, r is equal to rho over kappa. So this is going to become 3 rho squared over kappa squared plus 2 rho over kappa plus 1. Then you take the derivative with respect to rho twice. And you get, well, this term is going to disappear on the first derivative. This term is going to disappear on the second derivative. And so you get 6 over kappa squared when you take two derivatives. And so what's the original derivative with respect to r? Well, this term is going to disappear on the first. This term is going to disappear on the second. This is just going to become 6. And so it's evident. Psi r double prime of r multiplied by 1 over kappa squared is equal to psi r double prime of rho. And so, well, no, that'll make things too unclear. So I'm now going to make it clear whether something is with respect to rho or something is with respect to r, because things are going to get confusing in just a second. So you get well, 1 over kappa squared psi r double prime, we now know that that's just psi r double prime of rho. And then what's everything else? We get plus e squared minus e squared over 4 pi epsilon naught er. We will deal with that later. Minus, would you look at that? That's another kappa squared. Well, this would actually be positive kappa squared. So let's erase what's over this way. Multiplied by L times L plus 1 over R squared. Oh, would you look at that? That's just rho squared. So you replace the denominator with rho squared. And then the rest you have just minus 1, which isn't affected by the substitution. This is still psi r of r. Keep that in mind. You haven't done the substitution yet. But, if you really want to do the substitution, I don't think we can get a general form for it yet. Okay. There we go. So, this is what we're currently working with. Now, what else can we do? Well, we're first going to try to convert this to something of the form rho naught over rho. So how can we do that? Well, we already know that rho is equal to minus the square root of minus 2me over h bar multiplied by r. So that means 1 over rho, or rho naught over rho, is just equal to rho naught h bar over the square root of minus 2mer. And so, if that's equal to whatever was down here, minus e squared over 4 pi epsilon naught er, well then these cancel out, and we can get to work by writing rho naught is equal to minus e squared h bar over 4 pi epsilon naught e multiplied by the square root of minus 2me. Yeah, it's messy. That's the reason why we're abbreviating it as one constant. So we'll see this guy at the very end later. So now, what else happens? Well, we get psi r double prime of rho plus, this is now rho naught of rho over rho. This is L times L plus 1 over rho squared. Minus 1 is equal to psi r of r. Sorry, it's not rho yet. And so that is all equal to 0. So now, there's not much more to do except actually study the behavior of this function at asymptotes. We can't use power series, as I just said, and we've tidied up the function as much as we can, so we'll try to study its behavior and see what we can find out. So what happens as rho approaches 0? Well, this is going to stay constant, this is going to blow up, but this is going to blow up even more since it's an inverse quadratic, which means that this term is going to outshine all the others, and you're eventually going to be left with rho r double psi r double prime of rho is equal to minus L times L plus 1 over rho squared psi r of r. So now, for a moment, just to breathe, I'm going to unsubstitute rho here. So this is going to be 1 over kappa squared psi r double prime of r. And so, what is this going to tell us? This is equal to minus L plus 1 over kappa squared rho squared r squared psi r of r. So there we go. We can cancel out these guys, and it tells us that psi r double prime of r is equal to minus L times L plus 1 psi r of r. Now we make the standard power rule, over r squared. Now we make the standard power rule guess, because it looks like taking the second derivative of psi r decreased its degree by 2, which is standard for a monomial. So we take a r to the k as an ansatz for psi r, and then we get a multiplied by k multiplied by k minus 1. Is there supposed to be a negative sign there? I think I made a sign error. We'll just pretend that didn't exist and go on. K minus 1 is equal to L times L plus 1 over r squared psi r of r, which is a r to the k, and this is r to the k minus 2. Which means that since this is a r to the k minus 2, this cancels out, this cancels out, this cancels out, and k times k minus 1 is equal to L times L plus 1, which means that k minus 1 is equal to L, and hence k is equal to L plus 1. Which means that, well, there's technically an alternative solution, and that's r to the L minus 1, but keep in mind that that's, minus L minus 1. Keep in mind that's going to blow up as r approaches 0. It's going to look something like this, since L is a positive integer all the time. That's the conditions of the separation constant back when we solved for the other two equations 17 years ago. So, since we want a wave function that's actually integrable to satisfy Born's statistical interpretation, something that acts like this near 0 is not going to do it. And so we can only have one solution. This guy, right here. So, okay, I can drink water. Actually, hold up a minute. It's minus L, not minus L minus 1. I don't know why I said that. But my conclusion doesn't change. So, what do we get in the end here? And you can verify this for yourself. If you plug in minus L, you get minus L times minus L minus 1 is equal to L times L plus 1, and the minuses cancel out. So, that means that near 0, this acts like a to the r, a times r to the k plus 1. No, not k plus, to the L plus 1. So, now, since we're working around rho here, I'm going to rewrite this as a multiplied by, rho, r is rho over kappa, so rho to the L plus 1 over kappa to the L plus 1. But then I remember that kappa is a constant, and it can just be absorbed into a. So we now have a times rho to the L plus 1. And yes, a now changes with L. L is not changing over time. It's a constant. So it really doesn't matter. This is what we're currently working with. A rho to the L plus 1 is psi r of rho's behavior near the beginning. And also keep in mind that over the end here, when both were functions of r, we could have perfectly fine substituted in rho, rho squared, rho, and everything would be the same, but in terms of rho instead. Alright, so now we've analyzed its behavior around 0. What about its asymptotic behavior? Its behavior as it approaches infinity? Well, everything else is really hard to analyze because all three of these guys will play a part. So what is its behavior around infinity? Well, you get technically rho equals 1 wouldn't be so bad since this would just be a constant, but that wouldn't be interesting at all. It would just act like e to something of a function of this. So you get rho r double prime of psi r double prime of rho plus this disappears as you go to infinity, that disappears as you go to infinity, that doesn't disappear. So you get minus also, I realized that I made a sign error here. I feel like that's going to bite me in the back if I keep it around. So I'm going to quickly change that just to make sure I don't make it again. So psi r double prime of rho minus psi r of r, yes, we're still dealing with this, has to be equal to 0. So what can we do here? Well, oh, wait a minute. Wait a minute. Wait a minute. Oh, no, no, I'm not missing anything. All right. No, I'm not. I might feel. Oh, yeah, yeah. I'm getting mixed up with this equation and that. Sorry. So you get psi r double prime of rho, which I'll rewrite as 1 over copper squared psi r double prime of r, equal to psi r of r, and now I'm free to write 1 over copper squared psi r double prime of rho is equal to the same thing. And now this is just going to be the classic ansatz. Psi r is equal to e to the k r. So this is going to give us 1 over copper squared k squared e to the k r. Oh, sorry, e to the k rho is equal to e to the k rho, which means you get this cancels out, and k squared is equal to kappa squared, and so k is equal to plus minus kappa. And hence, that means that psi r around infinity, I do not like you. Psi r as rho approaches infinity is equal to e to the plus minus kappa rho. But now think about it for a second. Can we kill that?
Yeah, I'll try to pin it. Give me 1 second, I'll try to pin it. Where is it?
So e to the plus minus kappa rho, it gives us what? Well, if this is positive, if we take the positive root, that doesn't matter. If we take the positive root, then this is gonna, oh my god, it's back. Then this is gonna approach infinity. As rho approaches infinity, and it's not gonna be integrable anymore. And we don't want that. We want something that satisfies Born's statistical interpretation. So we have to take the negative root, which is a lot more tidy because as rho approaches infinity, this is going to approach 0. But what about when we're talking about rho is near 0? Well, remember, this is an approximation as rho approaches infinity. When rho is near 0, it's going to act like a polynomial. So that means that in total, rho is probably going to look something like this. But while we know its behavior at the beginning, and we now just learned of its behavior at the end, we do, minus kappa rho. Well, actually, when I think about it, this is e to the minus kappa r. I can't do rho without some consequences. So this is e to the minus rho. So since we know about this part's behavior and this part's behavior, but we don't know about the middle part's behavior, and we can't approximate it by guessing what all of the terms are going to be, then our only choice is to try to strip off all the asymptotic behavior by dividing psi r by rho to the L plus 1 so it stays around 0 here. Why did it turn transparent? Give us some information about the middle behavior and then go to 1 as we end. So that's the hope, right? But is that reality? So I'm going to define a new function. Psi r over line is equal to psi r rho to the minus L minus 1 e to the rho to strip off all the asymptotic behavior. But does defining that actually help? Well, the first thing we want to do is try to substitute it into the equation that we had before, which is over here. This boy. So we want to substitute psi r prime prime with something in terms of psi r overline prime and its derivatives. So, how can we do that? Well, the thing is, it's not going to be very advantageous for us to find psi r prime prime directly because as a function of psi r, because that's not what we're trying to do. We want to substitute it into here, and finding an inverse function of something so grotesque is going to be hard. Instead, we're going to write psi r is equal to rho times L plus 1 e to the minus rho psi r over line. And then when we take the second derivative, then we can actually substitute psi r over line as a function. We can actually substitute psi r over line and its derivatives into psi r prime prime and the psi r over here. So let's take the first derivative. And is that really gonna... Why do they have to do lawn work right now? Psi r prime is equal to, well, what happens when you... this is going to take a little bit. This is equal to, well, by the product rule, rho L plus 1 e to the minus rho r over line prime plus the derivative of this, which requires the use of the product rule again, as L plus 1 rho of L, rho to the L, e to the minus rho, minus e to the minus rho to the L plus 1 times psi r over line. Luckily, we can condense this by factoring out rho to the L plus 1 e to the minus rho, which will help us greatly in the future. So this becomes psi r over line prime plus L plus 1 over rho, notice because this is rho to the L, not rho to the L plus 1, minus 1, sorry, this would be in parentheses, times rho r over line. There it is, that's simple enough. So now, what happens when we take the second derivative this way? Well, we get psi r double prime is equal to, well, first we take the derivative of this, which we can just copy paste, L plus 1 rho L e to the minus rho minus e to the minus rho to the L plus 1. And then we multiply that by this without the derivative. Remember, we don't have to take the triple derivative. Everything stops right here. The pain ends here. Plus rho to the L plus 1 e to the minus rho r over line double prime plus, now you have to use the product rule on this guy. This becomes L plus 1 over rho minus 1 psi r over line single prime plus minus L plus 1 over rho squared psi r over line. And now, what we're going to try to do is first do the handy trick where we factor out rho to the L plus 1 e to the minus rho. And whatever's left inside is, first we cover this term. It's going to be L plus 1 over rho minus 1. Why did I say over 1? Times psi r over line prime plus, well, let's write it the blunt way. L plus 1 over rho minus 1 psi r over line prime plus L plus 1 over rho minus 1 squared psi r overline. And then you have the other term, which this gets factored out perfectly, and so we can just copy paste this. Before you go up, warning now, whatever goes up must come down. You'll get the peace from me. This won't be found. So what, just take me, man. Okay, so now let's try to condense this even further. This gives us rho to the L plus 1 e to the minus rho times, well, there's only one term with rho r over line double prime. There's a term with rho r over line single prime, two terms in fact. So this becomes 2 times L plus 1 over rho minus 1 rho r over line single prime minus the work of the devil. So this becomes minus, better way to write this, psi r over line multiplied by, let's do bigger parentheses in this case, L plus 1 minus rho squared divided by rho squared, and this is going to be minus L minus 1. Now there's a good way to simplify this. L minus plus 1 minus rho squared is just L squared plus 1 squared minus rho squared plus rho squared plus 2 times L times minus rho, which is minus 2L rho, minus 2 rho plus 2L. Okay, so that means this minus L minus 1 means this disappears, and this gets subtracted by 1. And we can condense that into L minus rho squared minus 2 rho plus L. It's not much, but it's something. Okay, so there we go. That's psi r double prime. Our mission is now to plug that back in. So, no, we're not done with the blackboard yet. We're pretty much halfway through. L plus 1 e to the minus rho. So this is psi r double prime. And so now we have God, I'm losing faith. Okay, now what happens? Well, you plug this in and you get rho times L plus 1 e to the minus rho multiplied by line double prime lots of time.
20 minutes, Cyril. Isaac, how long?
It's probably 20 minutes.
I'm so hungry too. Okay, Isaac gonna finish it in 15 minutes.
Okay. Psi r over line. Okay, there we go. I'm pretty sure that's it. So this is equal to, we bring that to the other side. L times L plus 1 over rho squared plus 1 minus rho naught over rho plus 1. And that is equal to rho r, psi r, which is actually psi r over line multiplied by rho to the L plus 1 e to the minus rho. Which is nice because we immediately get to cancel out these two factors. See, there is a legitimate use for factoring them out. So you get psi r over line double prime plus 2 times L plus 1 over rho minus 1 psi r over line single prime. The behemoth is coming. This is going to give us, well, we move this to that side. L minus rho squared minus 2 rho plus L. And then plus L times L plus 1 minus rho naught rho plus rho squared divided by squared. So that gives us what? Well, this reduces to L squared minus 2 rho L plus rho squared minus 2 rho plus L squared plus L minus rho naught rho plus rho squared, which means, yeah, there's a sign error somewhere. L squared, 2L squared plus 2L minus 2 minus rho naught plus 2 rho plus 2 rho squared. Yeah, that's everything. Minus 2 rho L. Yeah, it's supposed to be, to reduce it, it would be much nicer if everything here was a subtraction. Like if this was a minus, this was a minus, this was a plus, and this was a minus, then this reduces to what I should have gotten. Minus 2 rho L minus 2 rho plus rho naught rho. And I thought I fixed the only sign error. So where's that sign error coming from? Oh well, I don't have time to fix it now. So we just end it here.
Yeah.
Thanks everyone for watching, and we'll see you in the next one.